In this lecture, we're going to look at equations, three different types of equations, and how to solve them. Linear equations, and then quadratic equations, rational equations, and also non-quadratic equations that can be solved using quadratic methods. So when we have an equation where the variable that's in the equation is only being raised to the first power, so generally we don't even see a power, we consider that to be a linear equation. And generally there is one solution, or we should say at most one solution. Generally they take on the form ax plus b equals c. So you'll notice that the x there being our variable, a, b, and c are just real numbers, is raised to the first power even though we don't write it. But generally, we want to take the following steps as we approach this. Number one, if there are any fractions, so if a, b, or c are fractions, we want to look at all the denominators and figure out something that would be something that they would all multiply into. In other words, the least common multiple. This is the smallest factor that's going to contain all of the factors that are present in my denominators. And we're going to multiply both sides of the equation by whatever that LCM value is to clear out any fractions. And then second, if we have any values or expressions that are in parentheses where we need to do some multiplication, we want to go ahead and distribute all those and clear out any parentheses. So these first two steps are really to get it so that my equation has all the terms of the equation separated by pluses and minuses. Third, once I have all the fractions cleared and all the parentheses are gone, then we want to isolate the variable terms to one side of the equation, the constant terms to the other side. So as we're doing this, we're going through this process of addition and subtraction to both sides of the equation, and basically we're trying to combine all the variable terms to one side and all the constants to the other. And if we've done that successfully, step number 4, we're going to finally not just isolate the variable term that should already be isolated, but multiply or divide both sides by whatever would isolate the variable by itself. So we should have x equals something else. So let's look at a couple of examples. In this first one, I have two fractions. One of the fractions has a 3, one of the in the denominator, the other fraction has a 5 in the denominator. 6 is really, in essence, written over 1, right? It doesn't have a denominator. So we assume it being over 1, so I don't consider 6 as being a problem. But in terms of problems, there's nothing really wrong with having our fraction here. We just want to make it simpler and we want to get rid of it. So between 3 and 5, if it's numbers you're dealing with, I always go with the larger number and multiply it until I get something the smaller one or the other ones will go into. In this case, 3 doesn't go into 5. 5 times 2 is 10. 3 doesn't go into 10. 5 times 3 then is my lowest common multiple that they will both multiply into. So we're going to multiply both sides here by 15. Making sure to take it to each part here, each term is separated by pluses and minuses and equals. So I have 15 times x plus 1 over 3 plus 6 times 15, and then x minus 5 over 5 times 15. And so the 15 is going to each of these terms. So think of it as 15 over 1 when I'm interacting with a fraction. When it's with the 6 there, I don't need to really think of it in that way. But 3 does go into 15 5 times. So that leaves me, and 5 over here goes into 15 3 times. So this leaves me with 5 times x plus 1 plus 6 times 15, which is 90. And 3 times x minus 5. And then we can now get rid of. So I do want to point out here, though, that it's important. Notice that I have two terms on top of each of these fractions that you put parentheses around that and make sure that 3 is multiplied by every part in that numerator, right? It's not just 3 times the first number or 3 times just the second number. It's 3 times both parts of that fraction. So this would give me, as I distribute, 5x plus 5 plus 90, and then 3x minus 15. So each of my terms now is separated by a plus or a minus. Some are variable terms, some are constant terms. I'm going to get the variable terms to one side. So for example, if I want my variable terms to be on the left-hand side, I'm going to subtract the one that's on the right and balance out that subtraction by doing it the same operation on the other side. And since I want my constants on the right-hand side, since I've picked the left for my variable ones, we're going to subtract 5 and 90 to both sides. See, that gets rid of this, gets rid of that. I'm left with the numbers on the right, and now I've eliminated the variable terms on the right, giving me 5x minus 3x, which is 2x, and minus 15 minus 5, which is minus 20, plus minus 90, it's minus 110. Now I have the variable by itself almost. I just need to get rid of that multiplication by 2, so we do the opposite. We divide both sides by 2, and this leaves me with negative 55. And all things being equal, that should be the answer to the above equation. In a similar way, we don't have any fractions on the next one, but we do have the parentheses here that we need to get rid of. We need to clear those out. So by distributing the negative 7, I get negative 7t minus 14, and then 12t plus 3. So again, let's eliminate the variable term on the right, leaving it on the left. And then we'll add 14 to eliminate the constant on the left. That gets rid of this. That gets rid of that. So we're left with negative 19t equaling, keep on moving things around here, 3 plus 14, which is 17. And then dividing both sides by negative 19, we get t is equal to 17 over 19, and that's negative. We can either have the negative on the top or the bottom or out in front, either way, but this should be the solution of this linear equation. When we have second degree equations, or we call those quadratic equations, that means instead of the variable being raised to the first power, the highest power actually is a second power, which is why we call it a second degree equation. But these can generally be written in this form: ax squared plus bx plus c equal to 0, where a, b, and c are real numbers. They can also be 0, so it could be that we don't have this x term in the middle. So they could vary a little bit in the way they look, but as a whole, they should be able to be written in that form. And there's basically 3 ways that we can solve these, or 3 ways that we'll look at. The first is using the square root principle, and that's generally when we don't have this x term in the middle. And it's based on this idea that if we have the expression squared, or just x squared here, equal to some number, we can take the square root of both sides, and we're left with the positive and negative square root of the value over here. So the goal in using the square root principle, if we can, is to get the expression that's being squared isolated on one side of the equation. The second method we're going to look at is factoring. This can be tricky, but it also is sometimes a lot quicker than using the quadratic formula, which is the last choice we have here for solving quadratic equations. So using the square root principle, again, we can either have x squared isolated by itself and just a number on the other side, or I can have an expression squared equal to some number over here. Once I have the expression that is being raised to the second power, I can take the square root of both sides. But what I want to remember is that the square root of something squared just leaves me with the expression. But on the other side, we have to take into account the positive and negative solutions. If we started out with a squared thing, for example, x squared is equal to 4, this solution, or there should be two solutions to this. And when I take the square root of both sides, we can see, okay, and you may have already known, even without doing the step, that 2 is the solution. But for my original equation, negative 2 squared also would have given me, or would have resulted in positive 4. And so there's actually two solutions, the positive and negative. And that's what we want to always take into account. Whenever I take the square root of both sides to get rid of a square, I want to take the positive and negative on the other side of my equation. And always look for ways that this can simplify. The square root of 8 can be broken into, we look for perfect squares that might go into it, 4 and 2. Square root of 4 times square root of 2 is square root of 8. And 4 is a perfect square. And so that leaves me with 2 square roots of 2. So if I can, I always do want to simplify that, any square roots. And now it's just a matter of solving for x. To get x by itself, I would add 6 to both sides, so I have two solutions, 6 plus 2 square roots of 2, and 6 minus 2 square roots of 2. We can put these into our calculator to get the approximate values as well. And so 8.828 would be one decimal. That's 6 plus 2 square roots of 2. And on your calculators, if you go second enter, you can also toggle back now and go 6 minus 2 square roots of 2. That'll leave me with 3.172. Always look to what your question is asking for in terms of how many decimal points I want you to go. But these would be the decimal approximations. These are not exact answers. These are approximations. If I plug them in, I wouldn't exactly get the correct solution, but it would be super close. Whenever we round something, especially when it comes to radicals, we are dealing with approximations that are really close to the actual number because it's an irrational number that will repeat forever without a pattern. So we can't really take it any further than that. This would be the exact answer. This would be the approximate values. If we start off with something where the x squared part is not isolated, we need to make it so. So in this case, if I want to first just get rid of that subtraction of 7, that leaves me with 9, parentheses x minus 4 squared equals 19, or 18. And then I can also, in this case, divide both sides by that multiplication of 9. And so I end up with x minus 4 squared equaling 18 divided by 9, which is 2. Now I have the expression that was being squared, or raised to the second power, isolated. So at this point, I will take the square root of both sides. That leaves me with x minus 4 equals the positive and negative square root of 2. Adding 4 to both sides. To get x by itself, we have 4 plus and minus the square root of 2. Writing out the approximations then, we have 4 plus square root of 2, which is about approximately 5.414. And then 5 subtracting 2 roots of 2 gives me 2.586. Now, factoring quadratic equations is another way that we can rewrite them and solve them based in this principle that if I can write our expression as a multiplication, right, a times b, A factor, this is why we call it factoring, a factor is a part of a multiplication, right? So if I can rewrite this statement here, which is really a statement of summation and subtraction, right? If I can rewrite these as a statement of multiplication, what we're doing then is kind of unfoiling it, right? When we foil things, we tend to get this type of expression. We foil or multiply two binomials is when we get these trinomials. Anyway, we want to take that process and reverse it, rewrite it as a product, set equal to 0. This is key too. It has to be set equal to 0. It's called the zero product principle, where if we have two things multiplying to give me 0, either A has to be a 0, so 0 times some number B, or B has to be a 0 times some number A, or another 0. Either way, one of these has to be 0 in order for a product to come out as 0, and so we use that to our advantage, figuring out what's the value in here that would give me 0, and what's the value here that would give me 0. Okay, so I think this will be clear when we do this. You may have your own methods of factoring, and this is a whole other thing if you want to look it up and really get into a review of it. There's a lot of different video lessons out there. We're not going to get too into that because we're assuming at this point you know how to do this, but you may need to do some reviewing. It's easiest, of course, when we have a 1 here in front of x squared. So I have one of those that involves that, then I have a couple that involve numbers in front. But first things first, we always have to get it set equal to 0. And once I have that, then I do my double parentheses here, and I write in what I know. And when it's just a 1 here in front of x squared, I know that it just has to be x times x to give me that x squared. Looking at the last number, if it's positive like this one is, I know that gives me a clue. It tells me I'm either going to have a plus and a plus here, or it's going to be a minus times a minus. So I'm either going to have minus minus or plus plus. And looking at the middle term, I can say, aha, they have to be minus minus because the inners and outers add to give me that middle term. So I have to have two negatives to give me a larger negative, and then two negatives to multiply to give me a positive. Then this is a matter of figuring out what the factors are going to be in these last two spots here. And so I want to look at the factors of 15. In other words, 15, I can get 15 by multiplying what numbers? You can always use 1n, the number itself. Generally, that doesn't tend to be what the choice is, but it could be that. And then 3 and 5 are the other possibilities. 3 times 5 gives me 15. But we have to pair it up with what also we want in the middle, because again, this times x plus this times x needs to add up to give me negative 8x. 3 and 5 do that, since especially when they have the same sign. Only when they have the same sign, really. So we can see negative 3 times negative 5 is positive 15, and negative 3x plus negative 5x is negative 8x. And so I have this factored correctly. And so now I want to interpret this to look at my solutions. In other words, what number in this first parenthesis would give me 0 for that parenthesis, since it's x minus 3. In other words, x minus 3 will give me 0 for what values of x, and we can see this is a very simple equation. We don't even need to do this. We see that 3 minus 3 is what gives me 0, and x minus 5 equal to 0. We see x equal to positive 5. So I have two solutions for this particular one, 3 and 5. For this next one, again, it's set equal to 0. This is key. So we have what we need. I'm going to write in my double parentheses. Also, just like before, we have a positive number at the end here. But unlike before, I also have a coefficient in front of the squared term. So I have that to consider. Now 4 can either be 1 times 4 or 2 times 2. I'm generally going to start with the two that are closest to each other, and that's just a good practice. Why? Because it tends to be those numbers, and I don't know why, but it isn't always. I also know that I have a positive here, so that means it's either plus plus or minus minus, and because I have a plus here, I know it has to be plus plus. And then I have 2 as my last factor. What's nice for us is that it only has 2 factors, 1 and 2. And so putting these in, if I put 1 and 2 in there, checking my inners and outers, this would be 2t plus 4t, which would be 6t, and I need 9t. And even if I switch the 2 and the 1, it's not going to make a difference because they're both getting multiplied by the 2 in front. So sometimes we can switch those last two, and it makes a difference. But in this case, they're the same numbers or the same products, so we know that that's not the correct outcome. But it has to be 1 and 2, right? So actually, I'm going to leave those there. The ones I'm going to change out are the coefficients in front of t. I'm going to have to totally rewrite those. And let's try 4 and 1. This gives me 1t plus 8t, and 8t plus 1t is 9t, and so that gives me I know this is the correct order. And so 4t plus 1, if I want to look at what would make that parenthesis equal to 0, so 4t plus 1 equal to 0, subtract 1, 4t is equal to negative 1, and then t is equal to negative 1/4. For the other one, we can easily see that that's going to be negative 2. Negative 2 plus 2 is what gives me 0, so negative 2 is also a solution for this quadratic equation. This last one is not set equal to 0, so I do need to do one thing. Subtract 4 on both sides, which will leave me minus 4, and then we can set it equal to 0. And so now I have it, and we can start with the whole process. With 3, I only have one choice, 3 and 1, so I know it has to be 3u times 1u. But for 4, again, we have choices. It's either going to be 1 times 4 or 2 times 2. We have a subtraction here of 4, a negative number. That's the first time we've had that. The other two were positive. When it's a negative there, it has to be a positive times a negative. So it's either going to be plus minus or minus plus. I'm just going to put a positive and a negative in there. If I end up with the right answer but the wrong sign, I just know that the pluses and minuses are in the wrong spot. And then we have our choices for 4. I'm going to go ahead and start with 2 and 2. Again, it's not all the time, but generally tends to be the correct ones, the ones that are closer to each other. It wasn't on this one. It happened to be 1 and 4, but usually it is. And in this case, it works out. This is negative 6u and positive 2u. Negative 6 plus positive 2 is negative 4, which is what I have right there. So you'll notice there's a little trick too. You see that when I had over here 4t plus 1, the answer ended up being the opposite of this variable over the coefficient. So negative 1 over 4, negative 1/4. Negative 2 over 1t, so negative 2. So that's just kind of a shortcut. We can say u is equal to negative 2 over 3, negative 2/3, and then positive 2 over 1, so positive 2. Another way that we can always solve a quadratic equation is by using the quadratic formula. It just tends or can get a little bit messy with a lot of operations going on, but other than that, it's a surefire way to find the solutions. There are certain equations where we can't use factoring because our solutions may involve square roots or sometimes even what we call imaginary numbers. And so the quadratic formula is really the only way to solve for those. One of the only ones that we can use. So again, we want to first set it equal to 0. We always want to do that. That's whenever it's a quadratic, must always be set equal to 0. And so I'm going to do that first with this problem here by adding 8x to both sides. That'll give me, putting that term in the middle, x squared plus 8x plus 3 equaling 0. And now I'm going to use the quadratic formula here. If we tried to factor this, you would quickly see that it's not factorable. There are no factors of 3 and 1 that add up to 8, and so it's not going to work factoring. So we just have to identify the a, b, and c. And in this case, a is equal to 1, b is equal to 8, and c is equal to 3. You'll notice that a is the coefficient of the highest term, b is the coefficient of the middle term, and c is the constant. And identifying those, now we're going to plug them in. So it's always, you'll notice here, opposite of b, or negative b. I use the word opposite because it's a little bit easier to think of what the result should be. Because if b is 8, the opposite of 8 is negative 8. So I know that it's negative here. Having that minus there doesn't mean that the number there is always going to have a negative in front of it. If it was a negative, we would end up taking the opposite of a negative, which is a positive. And then it's b squared, so that's 8 squared, so 64, minus 4 times a, which is 1, times c, which is 3. All divided by, notice this line goes all the way across there, 2 times a, which is 1. So this is going to end up being 64 minus, and then 4 times 1 times 3 is 12. So 64 minus 12 is going to give me 52. So I have negative 8 plus or minus square root of 52. I like to kind of work out what that number under there is going to be and not have to rewrite everything constantly, right? So there's a couple ways of expressing this. We can take this 2. Notice it's negative 8, it's 2 solutions, plus square root of 52, all divided by 2, or negative 8 minus square root of 52, all divided by 2. You can also split this division up, making it negative 8 over 2 plus or minus square root of 52 over 2. Just make sure you take that 2 to each part on either side of the plus and minus there. That gives me negative 4 plus and minus square root of 52 over 2. And it's the square root of 52 divided by 2. We can't take 2 into 52 there and make it 26. That won't work. 2 is not underneath the square root, so we have to keep it out. But we will also want to get, as we did before, the 2 approximate values that this represents. These would be my exact solutions, this or this, because we didn't have to round any there. But let's go ahead and figure out what they would be as decimals. Plug these into your calculators now and see if you can get those 2 numbers. You may want to pause the video. These are the 2 approximate values of my solution, negative 39 tenths or 0.39 and negative 7.61. Hopefully you got the same thing. If not, go back and check the work. Make sure that that division by 2 is not under the 52. And if you wrote it this way, that you put this in parentheses each time and before you hit divided by 2 or hit enter. All right, let's move on to the next one. All right, identifying my a, b, and c here. We have a is equal to 4, b is equal to negative 20, and c is equal to 25. So, opposite of b, now that part is going to be positive 20, plus and minus the square root of b squared negative 20 squared is positive 400, minus 4 times a, which is 4 times c, which is 25. Well, 4 times 4 times 25 is actually 400. Oh, and this is all divided by 2 times a, or 2 times 4. And so that gives me 20 plus or minus square root of 0. This becomes 400 minus 400. 25 times 4 is 100 times another 4 is 400. So that gives me the square root of 0 over 8, plus and minus that. Whenever we have plus and minus nothing, square root of 0 is 0. I'm not really doing a plus or minus then, because 20 plus 0 is 20, and 20 minus 0 is 20. We're just left with 20 divided by 8, which is, well, this would be 10 fourths or 5 halves. Yeah, 5 can go into 20. Or sorry, 4 goes into 25 times, and 4 goes into 8 twice. And so in this case, we only have one solution, where back here we actually had 3. Of course, we don't have to approximate this. This would be 2.5, 2.5. Exactly. So that's not even an approximate. We only say it's approximate when we had to round it. But 5 halves is a terminal decimal. The last one we'll do here, I'm going to switch up the colors, so I should have broken it up before. But looking at my A, B, and C, I have A is equal to 2, B is equal to 1, and C is equal to 3. So opposite of B, so this is negative 1 plus or minus square root B squared. So 1 squared minus 4 times A, which is 2, times C, which is 3. All divided by 2 times A, or 2 times 4. So again, we have 8 on the bottom. Working this out, 1 squared is 1, so this is 1 minus, and that gives me 8 times 3, so 1 minus 24. I do want to point out that if either of these had been negative, if A, the 2 there had been negative, or the 3, then as long as one of them was negative, this subtraction would become an addition. Right? We'd have minus negative. But in this case, we don't have that. And so that's just 1 minus 24, which is negative 23. So I'm left with negative 1 plus or minus the square root of negative 23 all over 8. Now the problem with this is that this is a problem for us. We cannot have a negative under a square root. That produces something called an imaginary number. And so we would get a complex number answer here. And in this case, that means there's no real solutions. Sometimes we are going to express our answers with imaginary numbers. But in this case, we're just going to say there's no real number solution. And this essentially is saying that there's 2 imaginary numbers solutions. Sometimes it's described as 2 complex solutions, since imaginaries are part of the complex number system. We can also use these quadratic techniques that we've looked at, using the square root principle, factoring, and the quadratic formula, to help us solve some equations that are not quadratic, so they're not being raised to the second power, but they have a quadratic form. And the main thing we want to look at, or look for when we're doing this, is if they have a quadratic form, the power of the middle term will be half the highest power, right? So typically we have y squared and then y to the 1. Well, this follows that pattern. This is y to the 4th, and that's half of 4, 2. And so that's following the pattern. Also over here, we have 2/3, and then half of 2/3 is 1/3. And so this also will, we can use quadratic methods here. The first one we have here, I'm going to use this method called the U substitution, which becomes more important in calculus. And so that's why I'm going to go through this for this problem. And what we do is we just take the letter U, and why we choose U, I don't know. We just do. And we set it equal to the middle term, which not the whole middle term, just the y squared part. And so if U is equal to y squared, if I squared both sides of that, that would give me U squared here, and that would give me y squared, or y to the fourth here. Y squared squared gives me y to the fourth. And now you can see that temporarily at least, I'm going to substitute U into this formula, even though ultimately I want to solve it for y, not for U. This is going to be a holdover for a minute. So I get 2u squared instead of y to the fourth minus 9u, I accidentally wrote y in there, plus 4 equals 0. And now I'm going to solve this. If I can, I'm going to try to factor it. Let's see if this works. 2u, which means then I have a u. I have two negatives. And I think if I do this, I chose minus because I know I have a plus there. And then I want a negative product. So 4 and 1, this gives me negative 8 plus negative 1, which is negative 9. And so I know that this is the correct factorization of this. So my two solutions for U then are, and let's keep in mind these are solutions for U, 1/2, positive 1 over 2, and positive 4. But ultimately here, I don't want U. I was looking for the solutions for Y. So I have to take this one more step. If U is equal to 1/2, then I know Y squared is equal to 1/2. Oops, 1/2. And if U is equal to 4, then I know Y squared is equal to 4 because U is equal to Y squared. So I substituted out the U and put in Y squared, which now I can solve both of these for Y. This gives me Y is equal to the positive and negative square root of 1/2. And Y, doing it over here as well, that gives me Y is equal to plus and minus square root of 4, which is 2. I do want to point out that many times they don't allow us to have square roots on the bottom. So when I have the square root of 1/2, that's the same as the square root of 1 over the square root of 2. We have a problem with that at times. And we like to keep that bottom denominator value as a rational one. So I would need to rationalize this denominator. I can easily do that by multiplying the top and the bottom, which all I'm doing is multiplying it by 1. So it's going to have the same value. It'll take on a different form. But I chose square root of 2 because square root of 2 times square root of 2 is 2. And square root of 1 times square root of 2 is just square root of 2. And so the better answer here is positive and negative square root of 2 over 2. It has the same value as square root of 1/2, just in a different form without a square root in the denominator. For the next one, again, I'm going to follow the same process here. I'm going to use U substitution. And as you saw, I always took U and I set it equal to the middle term here, k to the 1/3. I'm just ignoring the coefficient at this moment. But then if I square both, if I square U, that's k to the 1/3 squared, which is 2 times 1/3, which is 2/3. Powers to powers, we multiply those. So that's 2 times 1/3, which is 2/3. So I have two values I can substitute out. This gives me U squared minus 2U minus 8 equals 0. And now I look for ways that I can factor this for U. I know it's going to be a double parenthesis, U and U, and it has to be positive and negative. And 4 and 2 multiply to give me 8, and negative 4 plus positive 2 is negative 2. That adds up to give me negative 2. So I see the solutions for u are negative 2 and positive 4. Now, of course, we're not trying to find u, we're trying to find k. So, and u is equal to k to the 1/3. So k to the 1/3 is equal to negative 2, and k to the 1/3 is equal to positive 4. I want this to be k equal to my solutions, and I can do this by raising it to the third power. 1/3 times 3 gives me, remember, powers to powers, we multiply those numbers, and 3 times a third is 1, so that's k to the 1 equals, in this case, negative 2 to the third, which is negative 8. And here, do the same thing. That gives me k equal to 4 cubed, which is 64. Now, we always want to go back, whenever I've raised something to a power like this, raise both sides of an equation to a power, sometimes I will pick up extraneous solutions. And that's because we're changing the power. You'll notice that, like with quadratics, we tend to have 2 solutions, right? Because the highest power is 2. With other equations, like here, we ended up with 4, right? Positive and negative square root of 2 over 2, positive and negative 2. And this was a 4th degree equation. Now with fractions, it's a little bit harder to see here, but the principle is whenever I raise an equation to a higher power, I tend to gain solutions that are extraneous. Now that doesn't mean it's going to be extraneous in this case, but it could be. So I'm going to start with negative 8. We're going to just plug it into our calculator. Negative 8 to the 2/3 minus 2 times negative 8 to the 1/3 minus 8 equals 0. So plug that into your calculator and see if we actually get 0 as a result of this operation. Now, you need to be really careful here. Number one, I use parentheses. You've got to use parentheses there, plugging that negative 8 in there. We want to raise negative 8 to the 2/3 power, negative 8 to the 1/3 power. If I don't have parentheses around that, it's only going to raise the 8. It's not going to bother with the negative. But it does work out in this case. You should get 0 as a result if you put it into your calculator correctly. I also want to point out that on a TI-80 384, the negative, you need to use the negative button that's under the 3, not the subtraction button. That will give you an error. This also works with 64 if you plug that in. Where we might run into problems, I just want to give you an example. With the 3rd power, we were okay by raising it to the 3rd power each time. But we would probably run into problems if I was squaring it and I had a negative answer. So at any rate, just be careful about that. Always double check if you ever, in the process of solving, have to raise both sides of your equation to a power. The last types of equations we're going to look at is rational, which is a term that we use to classify anything that could be written in a fractional form or could be expressed as a fraction. It's like whole numbers can be expressed as a fraction. 3 over 1 is a fraction. 0.5, the decimal 0.5, could be expressed as a fraction 1/2. But there are certain numbers, decimals that repeat for infinity without a pattern, which cannot be re-expressed as some sort of fraction. Some repeating ones have a pattern, and if it does have a pattern, those can be expressed in a fractional form. But regardless, when we say rational equations, we're really talking about equations that are inherently in a fractional form. And where we decide, this is a rational equations is when we see variables present in the denominators. So, as with linear equations, whenever we had fractions in our denominators, we wanted to figure out the LCM and then used it to clear out our denominators. We always want to get rid of denominators. They're a pain to work with, right? Also, with rational equations, you're going to see that all your solutions need to be substituted back. All your solutions need to be substituted back to check for possible extraneous solutions, but more so to look for solutions which cause our original equation to be undefined, meaning they result in 0 in the denominator. And we'll try to take that, but this is really important with rational equations. We always have to do that substitution. Sometimes we'll just do a substitution back in to check our answers to make sure that they're correct, that we didn't make any mistakes. But here we actually need to figure out, are they legit solutions? So we're going to look at 3 different types of equations here. The first one, actually 4, yeah. Couldn't remember how many are on the next slide. But I want to point out my denominators here. Notice that the t is in the denominator. This is where we have a problem. So, but in terms of the numbers that I have a 2, a 5, and a t. So looking at the factors, with the number 10, that's my largest, both 5 and 2 both go into it. So you always go to your largest and say, do the others go into that as well? And yes. So as far as what I'm going to use for my LCM, least common multiple or least common denominator, but we're using it as a way to clear out our denominators. 10 is going to be one of them. Again, we're looking for a multiple, something that all the others will multiply into. And the only other factor we have is t. And so that also needs to be a factor here in the LCM. So we always look for the number and then look for the highest powered variable or variable expression in your denominators. They also need to be factored before you try to find the LCM. And in this case, they are in a factored form. They're 2 times t, 5 times t, and 10 times t. Remember, a factored form is simply they're being expressed as a multiplication. All right, so this 10t, we're going to multiply everything by it. So it's going to go to each of the 4 things we have here. So 10t times 1 over 2t minus 10t, and you can put this over 1 whenever I'm interacting it with a fraction. I like to do that. This is over 5t, 2 over 5t, and then 10t over 1 times 1 over 10t. And don't forget the one that doesn't have a fraction. It also has to get multiplied as well. That's just going to be 1 times 10t. And now we can simplify this out. 2 goes into 10 5 times, and t goes into t once. So that simply leaves me with 5. Oops. No equals. For the second one, again, the t's cancel out. 5 goes into 10 twice. So I'm left with 2 over 1 times 2 over 1, which is 4. This just cancels out, so I have 1 times 1, so equal to 1. Or it doesn't become 0, it becomes 1. And this is 1, and then minus 1 times 10t. This has vastly, if you haven't noticed, simplified my equation. Over here, I have 5 minus 4, which is 1, equal to 1 minus 10t. And so solving this for t, you want to subtract 1 on both sides. That gives me 0 equals 10 minus 10t, negative 10t. Divided by negative 10, we see that t has to be 0. Now, looking at the equation that I actually have, the original one we have here, notice that if I put 0 in for t, that gives me a 0 in each of these 3 denominators. And that's never allowed. We can never have 0 as a result. Sometimes we can plug 0 in as long as it doesn't result in a 0 in your denominator. But in this case, it will, because it's being multiplied. And anything multiplied by 0 is 0. So that gives me 3 undefined terms there. And so this is not a solution because, and we checked for it, there is no solution here for this equation. The one solution we came up with is a illegitimate solution. And so here we would say there is no solution. All right, looking at my next example here, we see we have two identical denominator values of z plus 5. And so that expression, z plus 5, is the factor in those both of those denominators. It's not that z and 5 are separate factors, because they're not a part of a multiplication. They're a part of an addition, right? So we treat them as the factor of that denominator, and that's the only one I have. It would be like if I had two 5s down there, then 5 would be the only factor. If I had two x's, then x would be my only factor. Here, the expression z plus 5 is the factor, and so that's what I'm going to multiply both sides of this by, z plus 5, and that itself will clear out those denominators, and I'm left with z plus 4 equals negative 1. Subtract 4 on both sides, I see z is equal to negative 5. Negative 1 minus 4 is negative 5. And if I plug in negative 5, that's negative 5 in for z here. So negative 5 plus 4 is negative 1. And so I see that would give me negative 1 over z plus 5, negative 1 over z plus 5. The two sides are equal to each other. So z equal to negative 5 is my solution to this expression. No, it is not. I only plugged it in on top. Look what happens if I plug it in on bottom. We have a problem. Z plus 5 gives me 0 in the denominator. So again, just like previously, this cannot be a solution because, yes, it makes the top equal to each other, but it also, at the same time, gives us a 0 in the denominator, and so there would be no solution here as well. This is why it's important to check your answers especially for rational equations, answers that actually give me a 0 in your denominator. I'm going to work through a couple of more here. In this particular one, on the left here, we have one factor of x minus 1. And here we just have an x. So I see I also have a factor of x. This 3 doesn't have a denominator, it's just 1. So we just kind of ignore that. Now, I know they both have an x, but x is not a factor of the first fraction. X minus 1 is my factor. And so if I have different factors, like if I had a 2 and a 3, and they have no, or 5 and a 2, they have no relation to each other at all. They don't go into each other. Then we just end up multiplying them. In this case, my LCM is going to be the product of those two factors, not 5. I don't know why I have that, but x times x minus 1. This is my LCM. Right? When it all comes down to it, if we're looking for, trying to get a common denominator, we're not doing that here. We're actually using this to get rid of a denominator, but the LCM is the same as the LCD, the least common denominator. That's what we're trying to find. The least common denominator is the least common multiple. If they have nothing in common, then we just find their product. And then this is going to get multiplied by each part of the fraction there. So I have x times x plus 1 times x over x minus 1. And then we have x plus 2 over x multiplied by x times x minus 1 over 1. These are both over 1. And then here we have 3 times x minus 1. Cross out what we can. So here, the x minus 1 cancels. I'm left with x times x, which is x squared. Here, the x cancels, and I'm left with x plus 2, x minus 1. And on the right, we can distribute this. This gives me 3x squared minus 3x. It's looking like we're going to have a quadratic equation here. I also need to FOIL this out. Now, be careful of this subtraction here. when I FOIL this out, I need to keep it in parentheses because of the subtraction. X times x is x squared. X times -1, well, that's -1. -1 plus -1x plus 2x is positive 1x. And then positive 2 times -1 is -2. So I'm just rewriting everything here. But here what I want to do is to distribute this minus into the parenthesis. I'm not just subtracting x squared. I'm subtracting every single one of these. So think of it as a -1 getting multiplied through there. Once I've done that, then I can go back to what I had before. So this would be negative x squared minus x. Basically, they're all just going to change sign, plus 2. And now we need to get this solved for, we need to get it solved set equal to 0, because this is a quadratic equation. And I'm going to try to keep the first term positive. So I'm going to be wary of this and do whatever I have to do to keep a positive x squared. So I'm going to move everything to the other side, basically. We need to set it equal to 0, so we're going to add an x squared. This is x and minus x, so those cancel out, and then I need to subtract a 2. This will leave me with 0. And it gives me 4x squared. I have to subtract 2 as well. 4x squared minus 3x minus 2. And now we're going to see if this can be factored. If not, we may have to use the quadratic formula. I'm going to start off with 2x and 2x. And then I know it has to be, because I have a subtraction here, has to be opposite signs. So it's plus and minus. And 2 and 1. If I put 2 here and 1 here, is that going to work? This gives me positive 2x, negative 4x. Positive 2, negative 4 give me negative 2. I want negative 3x. So that didn't work. But 2 and 1, I know, if I switch these around, it's just going to give me positive 2 instead of negative 2. So I know what needs to change is the numbers out front here. It needs to be a 4x and a 1x. This will give me negative 8, positive 1. That doesn't work. That's negative 8, positive 1 is negative 7. I need negative 3. But because I have different coefficients now, instead of 2 and 2, I have 4 and 1. If I switch the 2 and the 1, I end up getting something different. This is positive 2, negative 4. And of course, that also does not give me, unfortunately, negative 4 and positive 2 is negative 2 as well. So that also didn't solve it for me. So to do this, I've got to use the quadratic formula. We'll take my C, my A is 4, my B is negative 3, and my C is negative 2. So opposite of B is positive 3 plus or minus square root. B was negative, so we take opposite sign. Opposite of B, negative of B, plus or minus B squared. So negative 3 squared is 9, minus 4 times A, which is 4, times C, which is negative 2. Now, having one negative here, if one of these is negative, exactly one of them is negative. If they're both negative, then we still just have a subtraction there. But if one of them is negative, this becomes plus. So I have 9 plus 8 times 2, so 9 plus 16. Yeah, which is 25, all over 2 times A. So maybe I missed something here. Maybe there was a way for me to factor this that I missed. But I'm just going to keep going with this. You guys probably were like, no. You should have done this. I'm just not seeing it off the top of my head, so I'm just going to keep going here. Yeah, because 9 plus 16 is 25. So this gives me, 2 times a is 4. Okay. Yeah, okay. So, sorry, I keep on wanting to fix this. So 9 plus b squared negative 3 squared. Yeah, that's 9 minus 4ac. So, yeah, 8 times 4. Oh, my gosh. Okay, that's where I'm going wrong here. That is not 16. So it's here I'm going wrong. I'm like going back and relooking over all my factoring there. Whenever we do get a perfect square under the square root, that means that was factorable. So that's what was happening there with me. I was thinking 4 plus 4 times 2, which is 16, but it's actually 8 times 4, which is 32. So 9 plus 32 is 41. That's not a perfect square. So I get 3 plus and minus the square root of 41 all over 8. And then let's go ahead and get those 2 decimal approximations. And I'm going to hit you should hit the pause, plug these in. It's really important to practice this. And you can see the 2 approximate values here. If you're getting something different, remember that this top part is a addition and a subtraction. You've got to have parentheses around it. And so literally I put parenthesis 3 plus square root of 41, close parenthesis, divided by 8. And then I hit cut and paste, so second and enter, went back and did the negative, right? Just changed the plus to a minus. And that gave me the second answer. So using that function on your calculator can be really helpful. You don't have to retype everything. You just swap out the plus for a minus. Going on to the second one here, I went ahead and just erased everything because I wanted a clean slate. As I'm looking at my denominators on this one, this is a much more, more difficult one, obviously. I want to go ahead and find the factors. Now, I know that x plus 2 can't be factored, 3x minus 1 can't be factored, but this trinomial can. It's important to me, I need to look at the factors. And my guess is, in this case, it's probably going to be minus 1 and positive 2, just because they're probably going to match what I have over here. And I'm just going to double check. That's negative 1 plus positive 6. Yeah, positive 6 minus 1 give me positive 5. So I know this is the factored form of the other 2 fractions. So looking at the LCM, I want to take the highest power of any common factor. And there's 2 factors of 3x minus 1. I have a factor here and a factor here. So we just take a 3x minus 1. And then I have 2 factors of x plus 2, so I'm also going to take an x plus 2. I don't have to take x plus 2 squared, and I don't have to take 3x minus 1 squared, because neither of these individually was squared. It's just if they're present. And then if there was any other factors present, I would want to take that as well. So if I had like a x out front, x would also need to be a part of the overall LCM. But all I had was these common factors, and so this becomes my LCM. This is going to get multiplied by here, so I'm going to try to squeeze it in here. It's going to be for the second one, and both of these are over 1. And for the third one, it's going to get multiplied 3x minus 1 over 1 times x plus 2 over 1. Right, so it gets distributed to each term. For this one here, it ends up canceling out both, and I'm simply left with the numerator, 4x squared plus 5. For the second one, the 3x minus 1 cancels, but I'm left with the other one, so I have 4 times what's left, x plus 2. But my denominator's gone. And here the x plus 2 is going to go away, and I'm just left with 3 and 3x minus 1. Now let's go ahead and distribute out here. On the right, we get 4x plus 8. And think of this as negative 3 that we're taking in. I'm going to make that plus negative. So don't forget to take the negative in with it. and that becomes minus 9x plus 3. And over here I have 4x squared plus 5. This is a quadratic because one of them is squared. So I need to, well, I like to keep the coefficient of the x squared positive. Just makes it a lot easier when you factor. So I'm going to subtract 4x. Just move everything to the other side. Add 9x. Subtract 8. And then subtract 3. This leaves me with 0 over here. And on the right, I have 4x squared. Negative 4x plus 9x is plus 5x. And then 5 minus 8 is negative 3. And negative 3 minus 3 is negative 6. Okay, so that's equal to 0. Let's see if this is factorable. I always check for factoring first because it's just easier. Start with the 2x and the 2x. Remember 4, we're looking at 1 and 4 or 2 and 2. I know it has to be plus and minus. And for 6, most likely it's going to be, could be 1 and 6, but it's probably going to be 2 and 3 if it is factorable. So I put those in first. Positive 4, negative 6. That doesn't work. And if I switch them, I'm just going to get the opposite. I won't, let's see, this gives me positive 4, negative 6, that's negative 2. If I switch these, the 2 and the 3, you'll see that because they're both 2's, it's just going to change which one is positive. We get negative 2, or positive 2x. So at any rate, that didn't work. So I'm going to go back here and change the 1 and the 6 and see if that, I always like to build from the back here. So if this doesn't work, go on to this one. And if this doesn't work, then we'll go ahead and change the y there and see if that'll work. So this would be negative 12, positive 2. Negative 12, positive 2, definitely not. That's negative 10. I need positive 5. Well, if I switch these, because they're both 2x, I just want to do this once so you can see. That's going to be positive 12 minus 4. And positive, oops, 6 and 1, sorry. So positive 12, negative 2, that's positive 10. So we had negative 10, now we have positive 10. All it did was change the signs, and that's because these are basically the same thing, just with different signs. Okay, so now in order for it to be factorable, I'm going to go back and we're going to start over with my 2 and the 3. I shouldn't have completely canceled that out. So we're going to take out the 6 and 1, and I'm going to go back to 2 and 3, but we're going to try it with 4 and 1. See, this is called chug and plug. Trial and error. It really is. So I'm going to try 4 and 1. And see if this works with the 2 and the 3. Now they're different. So if I do switch places, it does make a difference. 4x, it's just when they're the same. So this is 12x and then negative 12, positive 2, again, negative 10. Let's try switching those guys out. Put the 3 here and the 2 here. This gives me positive 3, negative 8. Well, positive 3, negative 8 is negative 5. I'm almost there, but I want positive 5. And so that tells me the only thing that I need to change here is the signs. If I make this negative and this positive, that gives me positive 8, negative 3. 8 minus 3 is 5. And so these are my 2 solutions. So I see the 2 solutions for x are 3/4 and -2. 3/4 and -2 are the two solutions, but I do want to check them. Notice that 3/4 is going to be okay. That doesn't give me a 0, but if I plug in -2, that will give me a 0 here and here, and that's going to be a problem. So 3/4 is a solution, but 2 is not a solution. And that brings us to the conclusion of this section, a quick review over solving linear, quadratic, and rational equations.